Hello everyone, those are still hungry for knowledge. This is my first video on space-time diagrams, and I'll just be going through the very basics of a space-time diagram. I won't even show you the axes of the primed axes or the axes of a moving reference frame, because I'm just really trying to get the basics of space-time diagram just drilled into you guys. Okay, so here is a space-time diagram of a stationary reference frame, and stationary reference frames are not moving, and it's commonly denoted by this capital S you see right here. And the special thing about these stationary frame space-time diagrams is that it just looks like a normal diagram that you see everywhere else in physics or math. And just like, for example, how in mechanics you have a graph that's, displacement in terms of time, this is just another diagram like that. Obviously a little bit more complicated because it's going to be about special relativity, but for now it's just like, remember the kinematics diagrams you learned a few years ago? It's just exactly like that. But few of you smart ones, you might notice that the axes are flipped around. In a normal kinematics graph, you got the displacement on the y-axis and the time on the x-axis, because the displacement, the position, the motion of the particle is always dependent on time. And because time isn't really but in relativity you have the y-axis as time and the x-axis as displacement, so it's the other way around. This is pretty counterintuitive at first, but you got to realize that in special relativity, time over here is just another coordinate. In normal physics, in classical physics as we know it, and in classical physics used in kinematics diagram, the only coordinates we have are x, maybe y, and maybe, if you're feeling fancy, maybe a z, because to represent 3D motion. Time isn't a coordinate. Time is an independent variable. But in special relativity, time is also a coordinate. And so if you're trying to be really fancy, space we can describe our world in a 4D coordinate, x, y, z, and time, and that's our 4D coordinate to describe our whole world in super amazing detail. But obviously we can't do that. We can't make a graph or a diagram with 4 axes. That's way too complicated. You can't achieve that in the 3D space we live in. More or less achieve that on a 2D piece of paper that we're going to write on. And so physicists decided for space-time diagrams, for the sake of simplicity, they decided to just consider one spatial coordinate and one time coordinate. So instead of using x, y, z, time as our coordinate system, we just use x, position, and time, which makes it a lot simpler. And so the only reason why we got the we got the position, the spatial coordinate at the x-axis and time at the y-axis is just to remind us that space and coordinates in special relativity is very different from classical physics. That's probably the only reason why we just said, physicists just wanted to make special relativity look a bit cool or something. I don't know. But anyway, some of you smart ones might be confused at the CT label of the y-axis. I also had this question at first because, okay, c is the speed of light and t is time. What's speed times time? That's displacement. So initially, me and like a couple of you, I'm guessing, are quite confused. Didn't you just say we have time as the y-axis? So why the hell is displacement now the y-axis? But I haven't really got a super satisfactory answer to this, but it's honestly just you can just think of this c as a constant of some sorts, like a scaling constant. Even if unit wise ct is described as meters, we don't really use this y-axis as displacement. We don't use this y-axis in terms of meters. We use it in terms of time. So honestly, just think of c as a scaling factor that just makes the graph look a lot prettier. And I'll go into depth about why we have this c scaling factor at first, but to discuss that, we gotta explore this term called a world line. A world line is just a line on the space-time diagram that shows the movement of an object. For example, let's jump to a kinematics diagram really quickly. When an object, we can use all kinds of different lines to denote an object moving around, right? We can do something like this, we can do something like that, we can do something crazy like this. Any kind of line we can draw, it correlates to a trajectory of an object in space and time. And if we want to show that an object is stationary, we show something like this. If we show it as something like this, a straight line, right? So how would you show on this space-time diagram something being stationary? Well, just remember that the space-time diagram is just the kinematics diagram rotated about 90 degrees. So if I wanted to show, let's say this is meters. If I want to show that an object is always at 3 meter, at the x equals 3 meter coordinate in our stationary reference frame, then I'll just simply draw a line. Oops. Like so. Simple enough, right? And that's called a world line. A world line is, again, just another line to show a motion or a position or the whereabouts of an object. Now, what about the world line of light? How would we be able to show that? That's for next video.